Mysterious bright flashes. Could this be signs of an alien civilization? Stay tuned for more. For a long time, scientists and ordinary people alike have been eager to imagine what life beyond our planet might be like. Any science suggesting the existence of something beyond has always been greeted with enthusiasm. Then came a turning point when the James Webb Space Telescope delivered clear indications of life somewhere in the cosmos. While scanning the depths of space, this powerful telescope detected something fascinating on Proxima Centauri b, a distant exoplanet. It observed light similar to those of extraterrestrial cities, raising the possibility that an extraterrestrial city exists on that distant planet. This idea has generated great excitement and curiosity among scientists, who are intrigued because a discovery could be one they have been waiting for. It suggests that there could be intelligent beings beyond our current understanding, organizing their societies in ways that we are just beginning to discover. Looking at these distant city-like lights located an incredible 4 light-years away, NASA engineers are amazed and wonder how long they have been visible in space waiting for our technology to evolve enough to detect them. David Kipping, an astronomer at Columbia University, described the planet where these lights were found as particularly complex. This is because, unlike most rocky planets that absorb sunlight and emit energy in the form of infrared, this exoplanet exhibits different behavior due to its unique relationship with its parent star, Proxima Centauri. This discovery made by the James Webb Space Telescope underscores its importance. The telescope's ability to capture infrared wavelengths was instrumental in detecting the unusual behavior of Proxima b, which is crucial to understanding the atmospheric conditions of this planet. Researchers plan to continue using this telescope to explore the atmosphere of this planet in depth and even investigate whether it might be habitable. The James Webb Space Telescope is especially sensitive to infrared light, which allows it to observe what's happening on Proxima Centauri b at night. For many telescopes, it is difficult to detect faint light in the vast darkness of space, but the James Webb can pick up even the faintest glimmers. This makes it an ideal tool for confirming whether the supposed city lights on the dark side of Proxima b are real. The telescope can detect any artificial light in space if it is within a very narrow frequency band, much narrower than the light emitted by normal stars. Proxima Centauri b has a dynamic relationship with its star. Its day side features solar panels capturing intense energy, while its night side is cold. The temperature variation on Proxima b, influenced by its atmospheric composition, is an intriguing topic for astronomers, and the JWST can effectively probe the planet's thermal emissions to provide crucial data on its atmospheric properties. Interestingly, the JWST's orbit around Earth coincides with the orbital period of Proxima b, allowing detailed observations of its daylight cycles to be made every 11.2 Earth days. If the planet has an atmosphere, the next step will be to examine its chemical composition to determine its ability to support life. Signs such as oxygen, water vapor, and methane would be indicative of habitable conditions. If these elements are detected, it would confirm its potential to support life. This would involve analyzing light passing through the planet's atmosphere, a complex task. Although the JWST is excellent for characterizing planetary atmospheres, it is primarily designed for other functions. It specializes in analyzing variations in the concentrations of water vapor, carbon dioxide, and methane. Despite its limitations in detecting free oxygen, a crucial sign of life, the telescope can also search for other important elements such as ozone, which indicates a healthy atmosphere. As scientists examine the data from the JWST, the search for distant worlds continues, bringing us closer than ever to discovering whether we are alone in the universe. It is critical to remember that the JWST can observe only a limited number of exoplanets closest to Earth. For more detailed atmospheric studies, astronomers will turn to ground-based observatories such as the Extremely Large Telescope, ELT, which will begin operations in 2028. The ELT is designed to offer a deeper look at the atmospheric structures of distant exoplanets, providing clear and detailed data on their potential to harbor life. In the meantime, the Webb telescope remains a crucial tool for the exploration of distant exoplanets. Despite its limitations, it continues to provide valuable information that could transform our understanding of what exists beyond our solar system both now and in the future. Researchers have big plans for future space telescopes. They want technologies that reduce starlight to better observe the planets around them, like using your hand to block the sun to see better. By dimming starlight, these future telescopes will be able to study the faint light reflected by exoplanets more clearly, helping to analyze their atmospheres and determine whether they may harbor life. However, this task remains a considerable challenge. Blocking starlight to observe exoplanets is easier said than done. Stars are incredibly bright, often outshining their surrounding planets by orders of magnitude, which makes it difficult to detect the faint light that planets reflect, essential for studying their characteristics. To tackle this problem, scientists are developing several innovative techniques. One such technique is the use of coronagraphs, devices placed inside the telescope designed to block out starlight while allowing the planet's light to pass through. By carefully shaping the light waves, coronagraphs can significantly reduce star glare, making dim planetary light more detectable. Another promising technology is the star shade, a giant flower-shaped spacecraft that flies tens of thousands of kilometers ahead of the telescope. It blocks starlight before it even enters the telescope, allowing only the planet's light to reach its instruments. This method could be particularly effective in observing planets in the habitable zones of their stars where liquid water and potentially life might exist. However, these technologies require extraordinary precision. The alignment of a star shade, for example, must be perfect down to fractions of a millimeter over vast distances. Moreover, these advancements must overcome space mission limitations such as miniaturization, energy efficiency, and surviving harsh conditions. Despite these challenges, the potential rewards are immense. Successfully observing and analyzing the atmospheres of exoplanets could lead to the discovery of biosignatures, chemical indicators of life. Molecules such as oxygen, methane, or water vapor in specific ratios might hint at biological processes, suggesting that life exists beyond Earth. Researchers are also exploring ways to directly image distant worlds in greater detail. Future telescopes could be equipped with advanced adaptive optics that adjust for distortion caused by Earth's atmosphere or telescope movement, producing sharper images. Combined with starlight blocking technologies, these improvements might allow scientists not only to detect exoplanets but also to map their surfaces and study their climates. The development of these next-generation space telescopes represents a leap forward in our quest to answer one of humanity's most profound questions: are we alone in the universe? By redefining our ability to observe distant planets, we edge closer to finding out if life exists beyond Earth, potentially revolutionizing our understanding of our place in the cosmos. As astronomers and engineers push the boundaries of what can be observed and understood, the tantalizing evidence captured by the James Webb Space Telescope opens not only scientific inquiries but also philosophical ones. If these bright, structured lights on Proxima Centauri b are indeed artificial, if they originate from urban-like formations, it would suggest that humanity is not the only intelligent species capable of altering its environment on a planetary scale. The sitter-like illumination captured on the night side of the exoplanet does not behave like the typical emissions from stars, moons, or even natural geological activity. Instead, it shows a frequency band, repetition, and thermal profile that raises more questions than answers. If we are truly witnessing artificial lighting from an alien civilization, we must ask, how advanced are they? How long have they been there? And if these lights have remained undetected until now, what other signs might still be hidden across the stars, simply waiting for the right instruments to reveal them? The notion that these urban-like glows might have existed long before humanity developed the technology to detect them introduces a humbling perspective. Perhaps the cosmos has always been alive with intelligence, activity, and expression, and we are just now beginning to see beyond the veil. The implications for science are equally profound. From astrobiology to astrophysics, from engineering to linguistics, every discipline would be called upon to contribute to a new understanding of our place in the universe. The discovery of potential intelligent life would not only expand the field of exoplanetary science but also force us to revisit core assumptions about the origin of life, the distribution of intelligence in the cosmos, and the likely pathways of technological evolution. Scientists would then need to develop entirely new frameworks to interpret potential signs of intelligence that are not human. How do we distinguish between artificial and natural signals when we only have Earth as a reference point? How do we determine intent, functionality, or complexity from distant thermal readings, fluctuating light curves, or transient shadows? The concept of technosignatures, observable evidence of technology that indicates intelligent life, would shift from theoretical musings to an urgent area of research. Urban illumination is just one type of technosignature. Others include radio signals, pollution patterns in atmospheres, or vast structures like Dyson swarms. Each of these would have to be reconsidered in light of real-world evidence, starting with Proxima Centauri b. One of the key next steps will involve repeating and confirming the initial observations. Peer-reviewed replication, using not only the JWST but also upcoming observatories, will be vital to validate the anomaly. Confirmation will lead to extensive modeling of the exoplanet's orbit, axial tilt, atmosphere, surface temperature, and any seasonal dynamics that might influence the visibility of such lights. Are the lights constant? Do they dim or brighten in predictable cycles? Are they geographically concentrated or distributed evenly across the surface? Answering these questions requires long-term, consistent monitoring, something that JWST can only partially provide due to its limited schedule and the high demand on its observation time. That's where coordinated international efforts come in. Multiple observatories, both space-based and terrestrial, will need to synchronize their efforts to build a comprehensive map of Proxima Centauri B's behavior over time. Future telescopes will play an even more vital role in advancing this research. Missions such as the Habitable Worlds Observatory, LUVOIR, and the aforementioned extremely large telescope will provide more powerful imaging systems, higher resolution spectrometers, and wider observational windows to collect data on exoplanets like Proxima b. With better tools, we'll be able to investigate